Okay, in this video we're taking up the worksheet that you just worked on in using Desmos. You graphed some functions, you answered some questions. Now I'm going to take up some of the questions, not all of them, just some of them, with these two goals in mind. The first goal is that I should be able to look at any polynomial function. Notice this is just any old polynomial function. It's a whole bunch of terms. One variable, all the varying powers of x. Okay, that's a polynomial function. I should be able to look at that and determine what the end behavior is. Okay, whether as x goes out to infinity, it's going up, or as x goes out to infinity, it's going down, or as I go to negative infinity, it's going down. So I'm looking at, say, these cases. I've got ending behaviors like this or like this. And just maybe some stuff going on in the middle, like we could have some of this stuff going on. So what we want to do is, I'm just concerned about the end behavior. Okay, are they going down or are they going up? So we could also have something like this. And you get the sense that we've got opposite endings. They go in the same direction of endings. They go in the same direction of endings. Okay, so that's what we're looking at. The other goal, after I go through some of this take up, is we should be also able to just determine the number of possible zeros a polynomial can have if I just look at the degree of the polynomial. Okay, so that's our second goal. Okay, so let's look at the first question you had. You had problem one. You should have graphed these two functions, f1 and f2. In Desmos, and if you get the sense, you just have to put the equation into Desmos as is, and it will graph it for you. So notice the black one is that cubic polynomial right there, and the blue one is this quintic, this degree 5 polynomial right here, this blue one. And sometimes you might have to zoom out or zoom in depending on which is like a pinching if you're doing it on an iPad or a device, or zooming out using the buttons on the computer. Okay, now I have to answer how these graphs are alike. Now there's not much alike. What I can though say is, especially when I look at the end behaviors, is notice as x as the black. Look at the black one. As the black one goes out to infinity, as x goes out to infinity, y is going up to infinity. And as x goes to negative infinity, y is going down to negative infinity. And this is the same for the blue one. Okay, so they both go, as x goes out to infinity, they both are going up. And as x goes out to negative infinity, they're both going down. Okay, so that's how they are alike. They have the same end behavior. Alright, and what we want to do is make notice this is a cubic. It has that kind of opposite end behavior. This is a quintic. Its degree is odd. It also has that same end behavior, which is the exact same as our power functions. If you think about the cubic power function, this is a slight change in that. And this quintic power function is way different, but the end behaviors are the same as the quintic power function. Okay, so they have the exact same end behavior, and they have odd degree. They're odd degree polynomials. Alright, so moving on, we had to graph these two functions, and here we go. We got the blue one this time is the first one, f3, and the purple one is f4. Okay, it says, how is the graph of f3 different than the graphs of the first two we saw? And f3 clearly has end behaviors that point down. Okay, so and both end behaviors point down. And the other ones did not have that. Okay. How is the graph of f4 similar to f3? So how are these two graphs similar? Well, they both have end behaviors that point in the same direction. And what I mean by that is notice the blue one, as x goes out to infinity, y is going to negative infinity, and is the same as x goes to negative infinity, y is also going to negative infinity. And f4, as x goes to infinity, y is going up, but it's also going up when it goes the opposite direction. Okay, now what characteristics of a function might affect its end behavior? Clearly the degree does, okay, because these are even degreed polynomials, okay, and they have the same end behavior. They go in the same way for both of these. So the degree clearly is going to affect its end behavior, is because the odd ones had opposite end behavior. So the degree affects its end behavior. And also we should be looking at the leading coefficient, the sign of it. And what I mean that is, notice this is F3 is a negative leading coefficient and these are pointing downwards, and F4 is a positive leading coefficient and they're pointing upwards. And this quadratic here matches what our degree 2 polynomial would be at a power function, so they point up. And this being a negative leading coefficient, and also in even degree polynomials, it's just upside down. So these are pointing, the end behaviors are pointing down. So these are the two things that affect end behavior, the degree and the leading coefficient, which is the exact same as end behaviors of just power functions, what we did before. Okay, so now what we want to be able to do is guess the end behavior. And so let's do this one first. This is just a power function. It's an even degree, but it's got a negative leading coefficient. So since it's an even degree, it should have end behaviors that point that go in the same direction, but normally they would point up. And since it's a negative leading coefficient, they should be upside down. So we could say as x goes out to infinity, y, it would have been going up since it's an even, but now it's going to be pointing to negative infinity. And as x goes to negative infinity, it would have been going up because it's even, but it's upside down because of the negative. Y is also going to negative infinity. Let's guess the end behavior here. Now, notice this has been factored. So if I imagine it being unfactored, like expand it all out, when I expand this part out, I would get an x, it would be squared, and then it's going to have a cubed. I get an x cubed out of that binomial right there. And notice over here, I'd have, if I expanded this out, I'd also get an x cubed out of that. And when I would multiply those x cubes together, I would get an x to the power of 6. So this is a degree 6 polynomial. And notice that x, if it was it was all cubed, and that x was all cubed. Notice these are positive x's right here. They would all be positives, and I got a positive x cubed times a positive x cubed if I expanded all that out, and therefore I have a positive leading coefficient. Therefore, those two pieces of information, since it's even, they would point in the same direction, and since it's positive, they're going to point up. So we can say as x goes out to infinity, y is going to go up. And as x goes to negative infinity, y is going to go down. Or sorry, it's going to go up. Okay, so let's take up the next part here. Explain how to determine the end behavior of the graph of a polynomial based on its degree and the sign of the leading coefficient. There are 4 cases to consider here. So say, let's start with it. We have an even. If we have an even degreed polynomial and a positive leading coefficient, so that's my positive, then we have it's going, the end behavior is going up, and say this end behavior is also going up. There's stuff going on in the middle, okay? Say we have an even and a negative leading coefficient, then we have it's an upside down. So as x goes out to negative infinity, it would be going down. Stuff's going on in the middle, and it would be going down as x goes out to infinity. Now if we had an odd degree polynomial and a positive leading coefficient, then as x goes to negative infinity, it's going down, and as x is stuff going on in the middle maybe, and as x goes out to positive infinity, it should be going up. In our last case, if it's odd and negative leading coefficient, this is reversed, so it should be, we've got this when it goes out to negative infinity, and it should be going down as x goes to positive infinity. Okay, we've got all this stuff going on in the middle. So that's what our 4 cases to consider. Okay, the last part of this video will be looking at the zeros. You filled this out for problem 5. You graphed each of these and you're just counting the number of zeros. And we want to be able to make a conjecture, like a guess, about the number of zeros based on its degree. Okay, so we've got a degree 3 polynomial. It had 3 zeros. Another degree 3 polynomial. This one had 2 zeros. This degree 4 polynomial had 3 zeros. This degree 4 polynomial had 4 zeros. This degree 4 polynomial had 2 zeros. And this degree 5 polynomial only ended up having 3 zeros. So did you make a conjecture about the number of zeros? Could the cubic have 4 zeros? No, it can't. So our conjecture and our reason, or our idea here is a polynomial can have at most the number of zeros as its degree. I'll write the poly for polynomial. The poly can have at most the number of zeros as its degree, which means that a degree 3 polynomial can have at most 3 zeros. Think about a quadratic. A quadratic, our most basic parabola, can have, it only had 2 zeros at most, but it could have had 1 zero, or it could have no zeros. But it had most 2 zeros, and that's going to be true for all polynomials. Look at this degree 4 polynomial right here. It had 4 zeros, but this degree 4 had 3, and this degree 4 had 2. It's possible for a degree 4 to have none. I want you to think whether it's possible for a degree 4 polynomial to have just 1. Think about those questions. Okay, so that's what we're trying to get out of here is it can't have, like if a degree 4 polynomial cannot have 5 zeros. A degree 5 polynomial cannot have 6 zeros. It can have at most as 5 zeros. So I hope you took some good notes and checked your answers. There's another video to watch and then a quiz.